want to go through the basics that you're going to be using. First is, if you have a function x of t, and it has a relationship to a Fourier transform x of omega. Now that's omega, and everybody, I believe, should know this. In electrical engineering, there are 2 to 3 things that are absolutes that you have to know well if you get out there for job interviews, because you're going to be dinged on one or more. One is digital. You have to know how to deal with digital circuitry, Boolean algebra, JK flip-flops, all that. The second is signals and systems. That is, you know how to do Fourier transforms, Laplace transforms, you know basically how to do things like partial fraction expansion, and all the things and the properties of the Fourier transform as well as Laplace. Parseval's theorem and some of the energy things you need to know too. These are things that they expect you to know, spectral density. And then for circuits, they expect you to know how to do RLC, transient problems or steady state problems, and transforms. I mean, that's in essence the absolute minimum when you get out there. And you will, I talk to students all the time that have graduated and have gone to various parts of the United States to take jobs. And in most of the companies that are higher end and high tech, they give you some sort of an interview process where you get problems thrown at you. Has anybody had this ever? You've interviewed, haven't you? How many have had jobs in the field? I mean, aren't you? Did they do anything where they examined to see if you were qualified? Anything like that?
Some do.
Not really.
No.
Not all.
When you have your degree and you go out there, they will do something like that. And I'll tell you some of the reasons for it. There's online universities, and there are universities that will allow all sorts of transfer credits from other schools that aren't really of the same, you might say, caliber. And they want to make sure what they're paying for. My brother told me a story, and this is when he was he still is there, at Dianetics. And they had a 4.0 from Auburn. This is just, maybe it's an anomaly, in business. And the guy was a disaster. He couldn't do it. Basically, they have one of these things where it's just fill in like scan sheets, things. And the guy knew how to do that. He knew how to get through the program. He had a very high average. He was horrible at what he was supposed to be good at. So I'm just telling you, they're doing stuff like that to weed out the people that are not qualified. Back to this thing. So x of omega, by definition, is simply the definition of the Fourier transform in the omega domain. It's x of t e to the minus j omega t dt. That is what I call its analysis. You're analyzing a signal for the frequency components. That's the general terminology. The signal that is real, that is actually something part of the realizable universe, is observing some phenomenon in time. You don't observe in the frequency. This is analysis. Then synthesis is when you take a signal in the frequency domain that you want. Usually think of these as transfer functions like h of t and h of omega. The impulse response of a system and the frequency domain spectrum, or I should say the passband, or the frequency domain characteristics of a system, linear system. And that would be 1 over 2 pi, the integral from minus infinity to infinity, of x of omega e to the j omega t d omega. Now those two are real important to understand. There's also the case where instead of omega they use 2 pi, or 2 pi f. And then you're going to get x of t here. Well, I'm just going to put it down for this one, or x of omega, or x of f will be equal to, that's the integral from minus infinity to infinity of x of t e to the j 2 pi f dt, minus j 2 pi f dt. Do you remember having this? Do you remember, did you do it in the omega domain or f domain? Anybody? Omega, in communications, Jachendra will do this. He'll have this, almost guaranteed. Now, I'm not gonna go through too much of this, but sometimes they put a 1 over square root of 2 pi here, and then they'll have x of t equal to 1 over the square root of 2 pi, and they'll have the integral from minus infinity of x of f e to the plus j times 2 pi f df, ft df. Now, I'm telling you these two I'm not worried about. What I'm concerned about is this and this, because we can always take omega and just say it's equal to 2 pi f. That's my big deal with this. So, having said that, we get this relationship. You should know some of the common things, and this is one thing I'm just going to mention because he does this in chapter 7 beginning. He'll have the common functions. Delta of t will go to, if you think about it, it just goes to 1. Do you remember this, class? All right, if you put a delta t in this, only value that's going to be non-zero at is when t is 0. When t is 0, e to the 0 is going to be 1. So you have something that has an area of 1 under it, integrated over that area, you get 1, and that's it for, and that is in the omega domain. Another one you're going to have is e to the minus at u of t, and this one I think everybody should know, a plus j omega. Now that's an important one. There's one you may not remember. Now remember, all these autocorrelation functions are going to be even. So this one happens all the time with spectral density. When you have e to the minus a times magnitude of t, here, that exists forever. If you look at that, what that one looks like is simply we have e to the minus a magnitude of t, and this is t, just looks like this. Has a peak value of 1. Basically, it's an even function. Flip it over, fold it across the vertical axis, and you'll see that it overlays. Y'all with me on this? Do you remember what the transform of this is? You can get it by just doing this, going from minus infinity to 0, and putting e to the at, because it would be, at that point, to make it a minus a, in front of there, it has to be, since you're in the negative domain, you have to make it e to the at, e to the minus j omega dt, or j omega and then dt, and then from 0 to infinity, it would have the same exact transform as this. But if you do that and mess with it, you get 2a, and then it's going to be over a squared plus omega squared. That's another one you should know. And finally, the pulse function, and I'm going to put it above this stuff. So what you may call a rect function of t over tau is really usually labeled a pulse function, and it has the transform of tau times the sinc of omega tau over 2. That's the first one that you should know also. And the last one you should know, or at least be appreciative of, and some of you haven't worked with this for a while, and this is the relationship between what I call the triangle function of tau of t. Now remember, this triangle function is nothing more than something that has a width of tau, and it's a triangle. That's all it is. That's the triangle function. This, I can write this mathematically if you want me to. This is, in fact, is simply equal to the quantity 1 minus, and it would be 2 times magnitude of t over tau times the pulse function of width t. So it only exists from minus tau to plus tau, or minus tau over 2 to plus tau over 2, and it has a peak magnitude of 1, and that's a mathematical equation for that state. Now that one has a transform of tau. I would give this to you, by the way, this transform and that transform. Some of these I'm not going to give you. Well, probably delta in this one for sure I'm not going to give you. And it would be times the sinc squared, and now it's going to be omega tau over 4. It's important to at least have an appreciation. It still has a sinc characteristic, but it's squared sinc, so it's all positive. This is strict positive, which means this, if it's an autocorrelation function, would give rise to that frequency domain component, and it is non-zero. One of the properties, not brought out in the book's discussion that much, but if you have any autocorrelation function and you take the Fourier transform of it with respect to tau, it has to be strict positive. If there's any negativeness in it, it can't be. And yeah, that's about all I have to say. This. Now, next thing is, when you have an autocorrelation function, call it Rx of tau. If we assume tau is like t, it transforms into the spectral density function. And it could be of f or of omega. Do you all remember that? Last time, and I gave you some simple problems or examples. When you look, there's, it's really, there's not a lot to be said. There's a couple things that happen with this. I'm going to use my notes here on this one. Well, actually, in the book, I forgot the page number this is on. I want to bring your attention to a formula. There's, you've heard of Parseval. Is Katie here? No. Has she, have you seen anybody? Do you know who I'm talking about? Has she been around at all?
Not this weekend, I think.
I don't know if she dropped or not. I didn't see it drop in the notice yet. So if she did, I don't see it. But this is the final day. 2, 4, 6, 8. We're missing 2.
Jackson.
Yeah, but there's a quiz. And her, okay. Well, we'll deal with what we deal with. So I want to just show you what this is in the book so you can label it. You're going to need, this is something I would know for the final. I would know for the final. And it's at the bottom of the page 259, and it's basically a simple theorem. Now I'm not going to go through all of it, but yeah, right there. What it's going to say is if you have time domain functions from minus infinity to infinity, and here I think he has x of t, or is it h of t? I forgot. Is it an
The
x?
one at the very bottom? Or,
Yeah, at the very footnote kind of thing.
he uses F and G.
F? F?
Yes,
And what?
G.
All right, g of t dt. And he's going to say that is equal to 1 over 2 pi, and there'll be an integral from here to here of, and there'll be f of omega times g of omega d omega. He should have this form. I think it's in the omega domain. Now, this is just one of many forms of these energy theorems. One thing I'm going to tell you, when you look at this, whenever I see two things multiplied together in one, pardon?
His says G of negative omega on the right
Yeah,
side.
all right, yeah, I'm assuming even, but, sorry. I'm sorry about that. Most of the, see, when I'm dealing with autocorrelation functions or anything like that, this is going to be even, so it doesn't matter, but I'm going to leave that alone. There's one more theorem I need to show you. Anyway, this is a relationship, and we're going to use that relationship. The one I think that you're most familiar with is Parseval's energy theorem that I'll just put down here. And if you take any signal, think of x of t as a voltage signal dt, and integrate it over all time. If you think about them like power in a resistor, assume you have a resistor of 1 ohm. I'm going to say this is my x of t voltage, and you have a resistor R equal 1 ohm. This is the way they talk about thinking about it. If you think about that, now x of t and 1 ohm, right? Well, what would be the current through here? The current I of t would be x of t, correct, class? I mean, if it's 1 ohm, right? Voltage over 1 equals current. Current and voltage are the same magnitudes, with me? Or same exact values, different units. If you multiply them together, you get the power. P of t would be equal to the magnitude of x of t squared. Do you agree with this? If that is the case, this is the way, with any type of information theory, you can assume R equal 1 ohm for all intents and purposes if you're an electrical engineer. You with me, class? Now, that's the power. If I want the energy, I have to integrate the power. Call I have to integrate the power P of t dt from over the existence of the pulse. Do you agree with that? That's what he's talking about here. That is energy. So I want to make sure you think about this as energy. Now, I don't know if I can prove this easily. There is a proof for it, but it has to do with the inverse first I'd have to take the Fourier transform of x of t, and then I'd have to square it, but I'm just going to tell you how to do it. Then what you have to do is prove that the value of the integral of the squared x of omega function, the magnitude squared, divided by 2 pi over all of the range of omega is equal to this. And it's a doable proof. I'm not going to do it here, and I don't think he does it in the book. He just makes it known. He says that's equal to 1 over 2 pi, the integral from minus infinity to infinity of the magnitude of x of omega squared d omega. That's one form of Parseval's theorem. Do you remember this one, Elijah? You mentioned Parseval's. Do you remember that one, or was it the summation one?
It was probably that one.
Do you remember this? This is Parseval's theorem. How many do? No, not sure I saw that for. You might have saw it with f. If it had x of f, there wouldn't be a 2 pi. That's the only difference in this. So, and that's one of it. Back to this thing. If f of t and g of t are x of t, you get x of t squared. And now, I'm assuming it's an even function, but that would take care of it even if it was odd. And this would be the magnitude of x of omega squared. Y'all follow me? So this is more general. Now back to the actual stuff. And the spectral energy density, last time, do you remember, if you can think of this right here, if you wanted the total amount of power, or what do you call it? If you wanted the mean squared values of the process, so x squared, it would be equal to the integral of s of f, he likes f, df from minus infinity over infinity. That would be the spectral energy density, and that would give you the mean squared value of the process. And if it was omega, then it would be 1 over 2 pi, the integral from minus infinity to infinity, of s x of omega d omega. We did a problem with this last time. Do you remember this?
So spectral energy density.
Yeah, and I want to tell you something. There are some tricks, because if we have a power function, what we have to do is say we're going to get the Fourier transform of the signal, but we have to divide it by capital T and take the limit as t goes to infinity to get it. If you think about this, if we have a power signal when we integrate it overall, now we have something where we have time up there. So you have to actually divide by capital T, yeah, and it will become a spectral power density instead of spectral energy. I don't want to spend too much time on this stuff, because remember, if it is a transient signal, y'all with me on this? If it is a transient signal, when you talk about the frequency domain components, it only exists for the duration of the pulse. Y'all with me? When there's no pulse, there's no spectrum. So we take a look at total energy in that pulse when we deal with spectral energy density. When we talk about power spectrum, we're talking about the continuous power in a signal, if it's got a whole lot of components. Just something to think about. The problem should straighten this out. So I want to do, I don't know if it's an example. What's problem 7-1.1? I think it's, yeah, I think this is it. Hold on. If I apply a lot of what I just said, it will make a lot more sense. Everybody here a junior? Anybody not a junior? Are you a senior? When do you graduate?
In the spring.
In the spring. Have you already got a job planned, or are you interviewing?
Look for one. Interview.
See me after class for a second. time of year, I will start getting requests from my brother, other people all around the country that I know that are looking for engineers. And they'll ask me specifically about people that I would recommend, and people, and if I don't think highly, I will not recommend people. But I have, especially one of my students who's my PhD student, is named Dan Fairclough, and he works for Iris. He owns Iris, and he does not want people that are problematic. And I will recommend some people too. Okay, for this one, 7-1.1. If you're interested, let me know. That's best for that. I'll talk to you after class. Okay. For this one, what does it say? X of t is a random process that, I think it's the one with m, right?
Yeah, x of t equals m, and the magnitude of lowercase t is less than or equal to capital T.
Yeah, so I'm just gonna do this. I'm gonna put the pulse function of, and oh, it's capital T, it's total width, so this is 2t, not t, of t. In other words, it's got a width of, tau is the total width, but he says the magnitude of that is gonna be less than t, right? So it's a total width of 2t. I think that's what he says, right? In other words, he's going to say it's equal to m right here for t less than capital T, which has got a range of 2t. Y'all follow me? This looks like this. So the total range is 2t, and that's why I put 2t right here. It's the only reason. And 0 else. Can everybody follow me on that? And he gives you something about m being a random variable, right?
Yes.
And he says that it's uniformly distributed.
Between -6 and 18.
Okay, so what he does is this. This is from -6 to 18 is going to be the values. And remember, this is a uniform distribution, so this height is going to be 1 over 24, or it's the spread. It's 1 over, basically width times height is area has to be 1. It's probability density. So they give you that. What does he want next?
The mean value of the random process.
All right, now this is important. When you look at this, if you have, he wants the mean value of this process, right? This has nothing to do with it. All right, he's talking about statistical mean at this point. If t, basically you could say for the mean value, if t is within that range, follow me, then you would have just m. So I need the mean value of m, and the mean value x of t would be equal to the mean value of m, and this would be for t less than tau. You can just do it this way. That should make sense to you. And it would be 0 else. The mean value of x of t would be 0 for anything else. So how do you get the mean value? It's just as before. If you look at that, the only thing you're going to do to get the mean value of m, which will be the mean value of x of t, is going to take 1 over 24. That is the probability density function. And integrate from this is the range, -6 to 18 of m dm. Now, does everybody understand what I'm doing? If you want the mean of anything and you have the density function, take that anything, say x times f of x, integrate it, dx over the range where x exists. And this is going to be what? 1 over 24, right? And then it would be divided by 2 m squared, evaluated from -6 to 18. Let's see, that's 1 over 24 times 2. And then you're going to have 18, which is 9 times 2 squared. And it's going to be that minus 6 squared. I did this last time, let's see, 24 times 2. I got 81 times 4 minus 36, let me see. Okay, so that becomes 2, that becomes 18. Now I got 162 minus 18 over 24. Anyway, you can tell me this quicker than I can. 144, wait a second, yeah. 144 for 24, 12, that's 6. Isn't it 6? Should know this. So it's 6, and that means, if you look at this one, it'll be 6 for the mean value for t less than capital T, and it'll be 0 else. Is that right? You got that?
Sure.
Part A.
It says 6 times the rectangle function.
Yeah, but that just says it's 6 if it's
Oh,
in its
yeah.
range. The rect t and pulse function are the same. Rect of t over capital T or t over tau is the same thing of pulse of t times. In other words, this function is the same as rect of t over 2t. Y'all with me? Right, it's the same thing. Okay, that's part A. What's part B?
The Fourier transform of the symbol function.
All right, of this function, of
Yes.
x of t, right?
Yes.
All right, now the Fourier transform has nothing to do with any statistical property of n. Assume m a constant. But if you look at this, what would the Fourier transform of this be? Now, this is the reason I put that stuff up at the beginning. I'm going to ask you. If you don't know it, don't worry about it. Just realize you're going to need to know, or at least recognize it. So remember when I put the pulse function looked like this, right? From minus tau over 2 to tau over 2, right? At a height of 1, and I call that either the pulse of tau of t, or you can call it rect of t divided by tau. Either one will get you there. The Fourier transform of that was the tau times the sinc of omega tau over 2. And here's the caveat that you have to understand. You'll get confused in his notes. It's the definition of the sinc function. So the sinc function that I'm using, and we will use, of x is simply defined as the sine of x over x. That's it. Y'all hear me on this one? The sinc function that is in the solution manual is the one that is used in some cases, and I'll put this way, I'll put sinc and a prime here of x is actually equal to the sine of pi x over pi x. Now, the obvious question is why? Why two different definitions of a common function, which is a bit confusing. Why don't I tell you one other place there's confusion? You know what a conjugate is? All right, well, and do you know what, you know what matrix determinants are and matrix inversions? You've heard of these things, right? You can invert a matrix. Well, in MATLAB, if you invert a matrix, you get the conjugate inversion. It doesn't say that anywhere. And in MATLAB, the other thing is log of x is actually not log base 10, it's log base e, it's ln. Y'all, these are things that can irritate, it irritates me because I find out about this accidentally when I get the wrong answer. Well, the sinc function is another one with MATLAB where they use that definition, sinc prime. Y'all hear me on this one? Now, why would they use this is the obvious question. Why do you use that? Just call this like f2 of x so you can see. If you plot x here and you plot this one, call it F1, right? Where does it go to 0? I mean, you can take a look at this, use L'Hopital's rule. At 1, it is 1. Do you agree with that? So we're just plotting now F1, but I'm going to show you. So it's 1. And it will be symmetric, and we'll do this. And where's the first 0 when you have that one? It would be, always look at the numerator. Where's the first 0 of a sign besides x equals 0? X equals plus or minus pi, right? So it would be here, pi. Now plot below that, plot F2. And I want you to see something. What is the value of this function when x is 0? Now you have to use L'Hopital's rule, right? Take the derivative of the top of pi comes out, right? With respect to x, you get a pi times a cosine of pi x, right? Take a derivative of this with respect to x, you get a pi. Do you agree with this? Pi over pi is 1. Same exact value right here. So for F2, you get the same value at 0. But where's the first 0 on that one? When x equals 1, right? Y'all see this? So that's the reason they do it. All the zeros are at integer values of the argument of the sinc function. That's the only reason. Otherwise, it drives you nuts. But that helps with plotting. Y'all with me, class? And in some ways, it helps with understanding for other reasons. But I use this one. The book in the solutions manual, without ever stating it explicitly in the book, uses this definition. Everybody with me? Now, this function has this definition, and this definition is the one I use, so that's tau times the sine of omega tau over 2. And it's going to be over omega tau over 2. Can everybody follow me on that? That's our definition. I just put the tau in there. You can see the tau cancels. Can you all see that? Now, having said that, if you look, what he's asking for is the Fourier transform of this right here. And I'm going to put it down there. And I'm going to use the definition of the sinc function that I have, and then I'll show you how it gets their definition. You all right? Just let me finish this thought. So they have a function m times a pulse with 2t of t. The m is scalable on either side. So m comes here. The next thing is tau, the width. The width is 2t. Do you all see that? So it's 2t. Then comes the sinc function, but I'll use that definition, and then we'll put it into his definition of the sinc function. Y'all with me? So I'll just use this one. So that's equal, and basically we can cancel that. The tau's cancel. Y'all see that, class? So if the tau's cancel, it's going to be the sine of omega. Tau in this case is 2t divided by 2, and it's divided by omega divided by 2. You know, everybody follow what I've done? I've literally just put in the sine argument for this because I want to show you how it goes to his definition. You with me? I'll give you a second. All right, now I'm going to modify this, and I think I'm going to leave it like, let's see. I want to get his definition, so let me just show you how I'm going to do it. First, I'm going to get rid of this 2, and I can see if I multiply top and bottom by 2, this becomes a 4. Right? Or I can put 2 here and 2 here. I'll do it that way, right? Now, his definition of the sinc function has a pi here. So what I'm going to do is replace omega with 2 pi f. It's in the f domain too. Can you all follow me? He's going to use a sinc function with this definition of sinc. This definition of sinc, but it won't have omega, it'll have f. Can you all follow me? All right, so when I do this, I get this becomes 2 pi f, and this becomes 2 pi f. 2 times 2t. I wanted to leave the 2 here because remember there was an omega over 2, so I have to multiply that by 2. Tau was already 2t.
Okay, but then we cancel the tau out.
Yeah, I canceled it. Did I cancel? Oh,
So that 2t wouldn't be there, right?
yes. Thank you. You're right. It's going to reappear in a second, but you're absolutely right. Let me actually move the 2m over further. So this is 2m. Y'all with me? Now look at his definition. He wants pi f in there. Let's see what we get. We divide by 2. Like that. I had that, I'm trying to modify it. So 2 goes away there. And I got my pi, so it's 2t. Now the reason I'm doing this, I know I have to have a pi, and whatever's next to it, see that x? There's a pi, there's an x. Whatever's next to it has to be down here. So I need 2 pi t, so then I multiply the bottom one by t. All right. I'm sorry, I'm put the pi out in front. And I have 2tf, so I have to multiply the top by a t. Y'all with me on this? I'm just trying to fit the form, can you see it? And let's see, 2tf pi, so I got pi. Yeah, that's it. So that means this would translate to 2mt, and this is going to be the sinc function that he defines, I'll put a prime there, of 2tf. And that means it becomes 2tm, yeah, should be it, times the sinc prime of 2tf. And he should have that in the answer, the solutions range. You see that? He's going to have a sinc, his sinc function, and it should have an argument of 2tf. And then he'll have 2tm out front. Yeah, all right, now I'm going to tell you this much. I'm not going to irritate you using that. All right, but the sinc function we'll use is this, and this is the fundamental definition. You just want to put the definition in. Y'all with me? So that would be the Fourier transform of the function. Does he have that? Yeah, he does. We're just looking at it, right?
For B, yeah, I just had.
All right, and what's the last part of that one, Elijah?
There's 2 more parts. There's the expected value of that transform.
Oh, okay. This is a little tricky. And I want you to know, this is why I was kind of reviewing Fourier transforms. And I'm going to do a Fourier transform property. This is really important. I want you to pay attention to this one. This one is golden too. It will save you so much in terms of angst. So if you think about Fourier transforms, there's a whole bunch of properties. Y'all remember? One of the properties is called duality. I don't know if you remember. And it says this explicitly. If you have some function x of t, and you know the Fourier transform of that function in the omega domain, this is a capital X of omega. We know that relationship. If you take that form of the function and you replace the omega with t, now it's important you understand this, and I'll give you an example, then I'm going to do that. Then you can take that and take this form of the time domain function and multiply it by 2 pi and put x of minus omega, and that will be the Fourier transform pair. Now it's called duality. Here's why it's so important. I want you to see this, please. Suppose I say we have a DC signal. I'm going to say x of t equal 1. You don't need to write this down, just be attentive. So I'm going to use the definition of the definition of the Fourier transform to get the Fourier transform of that. Okay? So the definition says x of omega is equal to the integral from minus infinity to infinity of x. It's just 1 times e to the minus j omega t dt. Can everybody follow me on this? So what is the integral of e to the minus j omega t dt? Well, it's 1 over e to the 1 over minus j omega, right? And then it's times e to the minus j omega t, evaluated from minus infinity to infinity. This would be t, correct? Anybody notice something strange about that? Well, expanded. So I have minus 1 over j omega, and then I have e to the minus j omega t minus e to the minus plus j omega t, and it's the limit as t is going to infinity. Does anybody know what that looks like? It's undefined. Take a look at this. These two are oscillating, plus minus, plus minus. It's basically going up and down between 1 and minus 1. Same with this thing. There is there's nothing that it's going to actually go to. It's just oscillating forever. No matter what, take t and add delta t to it. It goes up, down, down. There's nothing it goes to. But there is, and the funny thing is, there's this whole area of mathematics that talks about what happens to things in the limit. And they have all these tricks to do this. I don't know how they do this one directly, but I think they take e to the j omega t and expand it in a series. And they'll take e to the minus j omega t and expand it in a series. And you'll see the cancellation all the way down to the last term. It's a tricky, tricky proof, though. You all with me on this one? So I wouldn't mess with that. Here's the easy way. You come over here, and you notice, I'm going to use duality, so you notice delta of t goes to 1. So if I take that functional form, which is 1, it's not a function of anything really, 1, on this side, then I take this functional form, which is delta t, y'all see, on here, and I multiply it by 2 pi, and then I put times, I'll get out of your way, delta of minus omega. That's what the theorem says here. It's like nifty proof on this. Y'all with me? It says if I have 1, by the way, do you agree delta of minus omega is delta of omega? Because the only time it occurs to be, it will actually have a non-zero value is when omega is 0, which plus or minus 0 is the same thing. You agree with that? So just make it plus. So it means 1 goes to 2 pi delta of omega. Now it's real important to appreciate that. So in time, if you have a DC signal, in the frequency domain, all the frequency energy is at 0. It should make perfect sense in terms of how reasonable it is. Y'all with me on this? All right, back to this one. He wants the limit, and I'll just look at what he's asking. He wants to know what happens in the limit as t goes to infinity on this function, right? I'm going to erase this so you can see. I'm going to tell you, this is the kind of stuff that if you're getting into any kind of communication or information theory and stuff like this, you're going to be dealing with this kind of crap all the time. I mean, it's always one of these things you got to go back to the fundamental theorems to figure out what would happen. All right, what happens to this function as t goes to infinity? It looks like what? Basically, if this is the time domain, it is just what, 1, isn't it? Isn't that DC? What does 1 go to? 2 pi delta of omega. You also follow me on this? We just did that. 1 goes to 2 pi delta. That's what he's talking about. Now, if you try to do the limit over here with the sinc function in the limit, you know how he talks about you divide by capital, or you're going to have to take a look in the limit. As you got a sine t and a t going to infinity, you get one of these wacko things. It doesn't make sense. But if you go back to the time domain and look at what happens as the physical function becomes, the duration goes on forever, that's what you get. And is that the right answer? I think it is.
For part C.
Is that what it is?
The last one. Part C. 12T, so 2C.
No, this is the value of 1 goes to that. He wants the, what, the value of the function? All right, so what's going to happen is this. Since it goes to 2 pi t, we don't have 1, we have m, don't we? So there should be an m there. Is that right?
That looks more like the last part.
Didn't they ask for the Fourier transform of that?
The expected value of the transform.
In the limit as t goes to infinity, right?
That's part D.
Oh, that's 2 pi. 2 pi times
That
delta.
looks sort of like the last part.
Yeah, that's the
Yeah,
last
it's m times the impulse of half.
where.
That's the, it looks like the last part. that-
Yeah, but that's, yeah,
Oh,
that's,
I thought we were doing part C.
no, what is part C?
The expected value of the Fourier transform.
Oh, no, it's not the limit. I thought you said, I don't know why I thought you said the limit. All right, so the expected value of the Fourier transform. Here we go. The Fourier transform was, what was it, 2t, or 2, I'm trying to be sure. It's 2tm times the sinc of 2tf, isn't that right? Wasn't that his sinc function, right? And he wants the expected value of that function. Well, guess what? Expected value of something has nothing to do with this at all. It's really this. The sinc function, when the argument goes to 0, will be 1. Do you all follow me on this? So the expected value should be 2tm. Is that what it is? And the expected value of m is 6. So 12t. Is that what it is? But this is, he's just making you a little familiar terminology. When you look at the expected value in something in the frequency domain, remember in the frequency domain, it only exists when that time domain function exists. Do y'all follow me on this one? So frequency domain functions only can be talked about rationally when the time domain function is occurring. It has to be occurring, we can't even talk about it. If it is occurring, the expected value has nothing to do with any of the functions that are multiplying their functions of frequency at all. It has to do, well, it actually has to do with the frequency at 0, to be frank about it if you want to know. So at 0, that's 1, and it would be 2tm. The expected value of m is going to be 6, and t is just the width, undefined width. You follow me? And that's what he should have. So this should be the expected value of that. Whatever he calls it, the x, I think it's x of f in his, yeah. It's going to be equal to 2, it's really going to be 12t. I wouldn't ask you something that abstract. Then the last part is the, it's the, in the limit is capital T goes to infinity. The trick is don't do it in the frequency domain. It oscillates forever. Go back to the time domain and look what happens to the function. It just becomes 1. That's the reason. And you have to use duality to get. Now, what I'm showing right there has saved me so much angst and a lot of stuff over the years, over 40, 50 years of doing this crap. Because a lot of times you get weird signals that will not Fourier transform easily. Now you can use, if you have a finite duration pulse, you can get away with a lot. But an infinite duration, that 1 is an infinite duration. Technically, you can't take a Fourier transform of something that's not an energy signal, and one exists forever is not an energy signal, but you can do that trick and get it. Because of the area under the curve of the power is infinite, that's the reason. All right. That's it for that one, 7-2. Yeah. We'll do it real quick. I want to do 7.21. And then I'll stop. Anybody, didn't I put this stuff up? Did you look at this, anyone? Did you look at it? The problems aren't hard, but you'll notice they're tricky. There's some clever little tricks you need to know to do them. He doesn't show you these tricks and the solutions when you read them. So this is the last 7-1.2. Yeah, or is it 7.2-1?
2.1.
7-2.1, sorry, go ahead.
Use Parsifal's theorem to evaluate the following integral from negative infinity to infinity, sine of 4 omega over 4 omega.
So hold on, yeah. Oh, okay, this is kind of an interesting one. And it's sine of 8 omega over 8 omega.
Yes, sir.
D omega, right?
Yes.
This is ye old trick that I showed you in the beginning, where if you have the integral, now he wants Parseval, so if I have the integral of, I call it x of t times g of t dt from minus infinity to infinity, it is equal to 1 over 2 pi, the integral, and this is going to be equal from minus infinity to infinity of sine of 4 omega over 4 omega times the sine of 8 omega over 8 omega d omega, right? Now here's a trick. Don't try to do that integral. That would be foolishness. Think about one single thing. What I'm going to do is, you can see there's two functions multiplied together, and by the way, they're even functions, which means, remember, for Parseval's theorem to work, this would be minus g of omega. Matter of fact, I'll put it up here. So if you want the integral of, let me just do this. This would be x of omega, and this right here would be g of minus omega. But the minus omega doesn't matter because sine of 8 omega over 8 omega is in fact an even function. Do y'all follow me? Now bear with me 1 second. I'm going to get the g of t, and I'm going to get the x of t, but I'm going to do it in a simple way. I know for a fact when I have a pulse function with tau of t, I get a Fourier transform of tau times the sinc of omega tau over 2. I know I'm going to get it, right? And by the way, my sinc function's definition is going to be the sine of omega tau over 2 over omega tau over 2. Can y'all follow me? I'm trying to match that thing exactly. Y'all with me, class? Now, if this is the relationship that I know, in fact, exists, I'm going to modify it to fit that guy. Say, I'm going to do the 8 omega first. Now I'll do the 4. So I know I have 4 omega here. Y'all see that? That means tau over 2 is 4. Or tau is 8. Can everybody follow the reason? Right? All right, so now I'm going to put a 4 there. Over here, I have omega tau over 2. Tau over 2 is going to be 4, right? Can y'all follow me? And tau right here is 8. Y'all see that? Now I'm going to divide by tau. Let me get that middle one out. So I'll divide this by tau or divide it by 8. Can y'all follow me? And I'll put in right here 8. You with me? this relationship right here, right? Now, they don't want the 1 over 2 pi, so I'm gonna put 2 pi over here. I know you want your quiz, and you're gonna get it in 1 second, but I'm just showing you how to go about this, right? Now, here is what I'm gonna do. I'm gonna come straight down here, I'm gonna say this is 2 pi here, still the integral from minus infinity to infinity. That function x of t is gonna be p8 of t, sine of, the sine of 4 omega over 4 omega basically goes back to the time domain as this. I have to multiply this by 2 pi because it was 1 over 2 pi. That's the first one, I'm just gonna cut to the chase. The second one will be equal to p tau of 16 of t over 16 dt. Now this would be the integration that would have that value. Do y'all follow the reasoning behind it? The idea is, take each one of those single functions that are multiplying each other, get the inverse transform of it, the time domain function, then do this problem in the time domain. You do have to multiply by 2 pi. When you do this, what do you notice? Well, the 16 basically means it goes from minus 8 to plus 8, right? The 8 means it goes from minus 4 to 4, and it has values of 1. This one has no bearing. Do y'all follow me? It would be multiplied times 0 for this one, because in that range from minus 8 to minus 4, this one is 0. Do y'all follow me on this, class? So now my integration would go from minus 4 to 4. If you don't see it all, just work it out later. 4. And it would be simply this function. All right, now what is that going to be? Well, it's the area under the curve from minus 4 to 4 with a height of 1 or 8, right? And unless I did something wrong, this should be 16 pi. I sure hope I didn't forget anything. Did I get the right, wait a second. Oh, that was, hold it, I didn't, gotta make sure I divided by everything. This should be 1 over 8 times 16 downstairs, dt, and let's see what we get, dt. So that's gonna be 2 pi over 8 times 16 times 8. So that's going to be equal to 2 over 16, or pi over 8. Is that the answer? It is. But that's how you get it. All right, quiz. I want to tell you those problems, these problems, the first section of chapter 7, second section, you'll be responsible for 1 to 5. Can you all spread out too? I'm sorry. I wanted to get that out. But I wanted to make sure you saw that. That's a good problem, by the way.